want to go to school today. Oh, hi there. Didn't hear you come in. You're here a little early. Exponential growth. That's right. Hopefully you've completed the tables on this worksheet to the best of your ability, and you're ready to learn some new concepts. Okay, let's get to it. So starting with our Snapchat party, where we invite 3 friends and they invite 3 friends to the party and so on. You get a tree that looks like this. Notice how difficult it is to actually fit all those little invites in on day 3 even. And the table, completed table, looks like this right here. Notice in this table, the number of invites each day is tripling, timesing by 3 each time. You might also notice, even better, the pattern. Notice that each of these values is a power of 3, not just a multiple of 3, but a power of 3. 3 to the power of 1, 3 to the power of 2, 3 cubed, 3 to the power of 4, 3 to the power of 5. In fact, that pattern even works for day 0, because 3 to the power of 0 is equal to 1. So we essentially can come up with an equation here that the number of invites sent each day is just 3 to the power of d, if d is the day. I mean, you could also say y equals 3 to the power of x if you just wanted to use y and x. It's up to you. It doesn't really matter. I use d and n there. If this pattern continues, can you determine how many invitations will be sent on the 10th day? Well, yeah, well, d equals 10. So that would just be equal to 3 to the power of 10, which I'm guessing is a pretty big number. 3 to the power of 10 is 59,049 invitations sent on that day alone. We're going to continue looking at the other examples, and we're going to work with this pattern here and show how that pattern can give you the equation, which is the ultimate goal in these examples. Let's move to the next one. So a contagious disease. 3 people in a town have the disease, and every week each of these people infects 2 other people. So the tree would look like this when completed, and our table of values, you have 3 people week 0, each of them infects 2 people, so that's 6 people after week 1. Each of those 6 people infects 2 people, so that's 12 after week 2, and that pattern continues, 24, 48, 96, and so on. Now, we're doubling each time. Okay, so each of these is times 2. However, these are not powers of 2. It's not as simple as the last example. But I'm going to show you how we can relate the week to the number of new infections and then make a similar prediction for, say, for week 10. You're doubling each time. Let's take an example like 24. How did I come up with the number 24 here? Well, technically I started with the number 3, and then I multiplied by 2, 1, 2, 3 times. So technically the number 24 is 3 times 2 to the power of 3, or 3 times 8, which is 24. For week 2 at 12, I took the number 3 and I multiplied by 2 twice. So that's actually 3 times 2 squared. That pattern continues. 3 times 2 to the power of 4 will give you the 48, and 3 times 2 to the power of 5 gives you 96. 3 times 2 to the power of 1 will give you 6, and in fact you can even use the pattern for week 0 and say that that is 3 times 2 to the power of 0, and since 2 to the power of 0 is 1, we do get the correct answer. So if we wanted to make a prediction like week 10, we could say that the answer is going to be 3 times 2 to the power of 10, and what do we get for that? I think 2 to the power of 10 is 1,024, I believe. Yep, times that by 3, you get 3,072. Those are the new infections each week, not the total. The total would be more. So that's one way of looking at it. You can use this table to get that pattern. You could also see that pattern if you realize these are like powers of 2. Okay, 1, 2, 4, and the next one would be 8, and so on. However, there's 3 of them. The equation here for the infections per week would be y equals 3 times 2 to the power of x, where y is the number of new infections that week, and x is the week number. You'll often see that written like this: y equals 3 bracket 2 to the power of x, or sometimes the brackets are around the 3. Okay, let's look at the next example. So in the grocery store example, you're starting at $15.25 an hour, but you're getting a 4% raise each time. And here I walked you through how we can quickly figure out what your pay will be next year. Rather than adding 4% to $15.25, it's much quicker to just multiply by 1.04 to get that $15.86. And the reason that works is you're basically saying you're getting 104% of your pay for the next year. Or you could look at it this way. You could say for every dollar you make, $15.25, you're now going to make $1.04 because that's a 4% raise. Using that 1.04 allows you to fill the table out, and here I've shown it to you. Now, if you're off by 1 cent in a couple of these examples, that's okay. I mean, there's rounding that happens, and depending how you do it, if you round and then multiply by 1.04, or you take the unrounded number and multiply by 1.04, then you might be off by 1 or 2 cents at the end, and that's not important in this example. What is important is the pattern, because the pattern is going to allow us to answer this question of 20 years without going through and multiplying by 1.04 20 times. Actually, think about what I just said there. You don't want to have to multiply by 1.04 20 times. Well, that's what exponents are. They speed up that process for you. Let's take a look at, for example, if I look at year 2. What have I done to get 1649? Well, I've taken 15.25 and I've multiplied by 1.04. I've done that 2 times, which is the same as saying 1.04 squared. And here I've got 1525 times 1.04 to the power of 3. 15.25 times 1.04 to the power of 4. And that pattern works here too. 1525 times 1.04 to the power of 1. In fact, it even works here for year 0. Since 1.4 to the power of 0 is equal to 1. You just get 1525. Oh, and the last one, of course, 1525 times 1.04 to the power of 5. Well, how do we get it in 20 years? Well, we can follow the same pattern. 1525 times 1.04 to the power of 20 should give you about $33.41 per hour. Not too bad. We can also come up with an equation for this. Let's use N for the year. Number of years, it's common to use N for that, and W for the wage. Well, the equation of this relationship is W equals 1525 times 1.04 to the power of N. Sorry about that. And there's your equation. Take a look at the next one. We're going to talk about bald eagles now. They were almost extinct back in the 90s and the 80s and 90s, and they've made a big return since, and this is about how their population's growing. They're a giant eagle. If you've ever been lucky enough to see one, you do see them around here sometimes. Did you know that their nests weigh a ton, like literally weigh about a metric ton? They build the biggest nests of any animal there is. Okay, so in this case, we've got our nesting pairs of eagles increasing by 6.8% each year. So if you wanted to calculate the new number of nesting pairs each year, then you can multiply by 1.068. And that's exactly how I got these values here. Now again, if you're off by a little bit, that's okay, because there's 2 ways you can do it. You can multiply the rounded numbers by 1.068, or you could leave the number with the decimal places on it and multiply that by 1.068. And depending how you do it, you eventually at the end, you might be off by a little bit, and that's okay. That doesn't really matter in this example. Now, how do I get a pattern or an equation so that I can answer question 3 here, predicting the population in the year 2015? Well, let's look at 1997, for example. How did we get 4,756? Well, we took the number 3,000, and each time we went down, we multiplied by 1.068 for 6.8%. And by the time we get to 1997, we've done that, of course, 7 times. So in 2015, if we wanted to know that answer, we could take the number 3,000 and we multiply by 1.068. And of course, in 2015, that would now be 15 years. So I'm going to pull my calculator up and see what does that number give me. Okay, 3,000 times 1.068 to the power of 15. We'd expect to see about 8,048 as an estimate. Now, how about an equation here? Well, let's use n for the year again. And let's use p, because it's kind of like a population here. So the population of nesting eagles would be 3,000 times 1.068 to the power of n. Now, what is n in this case? Well, in this case, n is the number of years since 1990. So one option, I mean, this is fine for a formula. You could write that as a formula, and then you could just explain, look, P is population, and N is number of years since 1990. Or you could do something like this. You could say that it's 3,000 times 1.068 to the power of N, take away 1990. So that this way, N is now the year. So you plug in 2015 into the formula, and you end up subtracting 1990. And hey, even better, let's use our function notation, P of n. So those previous examples all looked at exponential growth. You can see some of the characteristics of exponential growth. You're always multiplying by something. In the first example, you're timesing by 3 each time. In the second example, you were multiplying by 2 each time. In the grocery store example, you're multiplying by 1.04 each time. And in the bald eagle population, you're multiplying by 1.068 each time. Also, each of the equations involved an exponent as well. And in fact, the independent variable, or the x variable, actually appeared as the exponent in the equation. Now we're going to move on to exponential decay. And these are not going to be examples where things are growing exponentially. They're actually going to be decaying or going down exponentially. Consider the 2018 BMW M2, valued at $65,000, depreciating or decreasing in value by 20% each year. Well, if the car loses 20% of its value, then it retains 80% of its value. Therefore, we can multiply each year's value by 0.8, and that's exactly what I've done to get these values here. To get 52,000, I took 65,000 and I multiplied by 0.8. And similar to the examples with exponential growth, this pattern emerges. How did I get a number like 26,624? Well, I took the number 65,000, I multiplied it by 0.8, 1, 2, 3, 4 times, or 52,000 times 0.8 to the power of 4. In fact, the pattern even works for year 0, since 0.8 to the power of 0 is equal to 1. Nice thing about our rule for the power exponent of 0. It helps us in an example like this. The equation of this, by the way, if we let the year be n and the value of the car be v, then we could say that v is equal to 52,000 times 0.8 to the power of n. Okay, next example, Detroit City. Detroit's one of the only cities in North America to experience population decline. Starting with a population of 950,000 in 1999, we're going to say the population decreases by 1.5% each year. Well, how did I fill out this table? I multiplied everything by 0.985. Why does that work? Well, look at it this way. If I take 100% and I subtract 1.5%, I get 98.5%. That's the population, or the amount of people that actually stay in Detroit. Kind of an optimistic way of looking at it. So each year, there's 98.5% of the previous year's population still there. And so a number like 935,750 is really just 950,000 times 0.985 to the power of 1, or just 0.985. The next year, I take that value and I multiply it by 0.985 again, and this pattern of powers is going to appear again. So very similar to before. Here's that same pattern, like I said. So by the time we get to 2005, we've taken 950,000 and we've multiplied by 0.985. We've done that 1, 2, 3, 4, 5, 6 times, or 950,000 times 0.985 to the power of 6. Again, the rounding, you might have different numbers slightly because depending how you rounded along the way, don't worry about that, it doesn't matter. You could be off by a few people and that's okay. So, what about an equation for the population of Detroit? Well, we can use this pattern and we can see the population at year n is equal to 950,000. 950,000 times 0.985 to the power of, and I'm going to take n and I'm going to subtract 1999 so that I can actually plug in the year into my equation. Now, how about a simple question, like a kind of a, seems like sort of an obvious question, what about the population in the year 2020? Well, we would take 950,000, multiply by 0.985 to the power of, okay, 2020 minus 1999 would be 21 years. I'll use my calculator to see what I get. That's about 691,647. So 691,647. There we go. And of course, a good question would be, how close is that to the current population? I do believe that 950,000 is very close to the real population in 1999. And there we have it on this website. Their estimate for Detroit's population right now is 667,000, so actually a little bit lower than what we got even. Population decline causes all sorts of problems in cities, but that's a much bigger topic. Okay, let's take a look at summarizing this information. So here were the 6 examples that we did. Why don't you go back and quickly write each of the equations beside each of the explanations I've given you. So I've gone ahead and done that for you here as well. My exponential growth all in blue and my exponential decay in red. And you notice that the explanation I've given you is all I actually need to come up with the equation. Contagious disease, 3 initial infections, number of infections doubles each week, 3 times 2 to the power of x. Grocery store job, $15.25 an hour, increase of 4%, 15.25 times 1.04 to the power of n. In each case, it's actually possible to see the relationship between the equation and the information given to you. All I'm really giving you in each case is an initial amount and then what I call a growth or decay rate. Even in the first one initial invitation, we could think about there being a 1 in front of this. So all these equations actually have this form right here, y equals a times b to the power of x, where a is the initial population or the initial amount, and b is always the growth or the decay rate, growth rate for the first 4 and decay rate for the last 2. And then the y value will give you the population or the amount, whatever it is at time period x. Let's just take a look at, before we answer this question about what the graphs would look like, let's just look at a simple example. The population of rabbits doubles every year in Mr. Elliott's backyard. This year, Mr. Elliott counts 20 rabbits. How many rabbits will there be in 3 years? Well, basically, to figure out the number of rabbits in my yard, you can take those 20 rabbits, and our growth rate is 2 because they're doubling. Y equals 20 times 2 to the power of x is an equation that represents the number of rabbits, y, based on how many years have passed, x. So in 3 years, that answer is going to be 20 times 2 to the power of 3, which I believe is going to be 160. And in 10 years, it's going to be 20 times 2 to the power of 10. $20,480. Consider a school board that has 58,500 students in the year 2020. And the students are expected to grow, the student population will grow at a rate of 2.1% per year. So how do we come up with an equation? Well, we could say the population based on the year where N is the year and P is the population. Take our initial amount. The growth rate is now, well, 2% is 0.021. We're going to add 1 to that to get 1.021 as a growth rate to the power of N, and I'll go N minus 2020. So that N is the year and P is the population. All I'm doing is using this basic formula where A is my initial amount, 58,500, and B is my growth rate, in this case 1.021. And then I change Y to P of N and X to N. So in 2025, P of 2025 is going to be equal to 58,500 times 1.021 to the power of 2025 minus 2020 will give you 5. I can use a calculator to come up with that answer. Sometimes I like to start with the growth rate part. 1.021 to the power of 5 equals that, and then I multiply that by 58,500, and we get 64,906 approximately. I usually round to the nearest person in this example, but it doesn't really matter. It's just an estimate. Now, the next one, how about the year 2014? Notice that's before 2020. Well, actually, our equation is still going to work. Sorry, 2014. We are going to have a negative exponent. When we sub that in, we will take 2014, subtract 2020, and we'll get our exponent of -6. This is actually going to work. Our definition of negative exponents meant dividing instead of multiplying. So imagine instead of going down the table, imagine you went backwards through the table. Instead of multiplying by 1.021 each time, you divide by it. Now to actually get this answer, we can just calculate this on our calculator. 1.021 to the power of -6 gives me that, and I multiply that by, notice that's less than 1. And sure enough, I get a number less than 58,500, 51,642. And there we go. Now suppose we have a different school board with an initial population of 63,200, but this student population is going to decrease by 2.1% per year. So now we're talking exponential decay. So the equation in this case is our initial value, 63,200, but now we needed a decay rate. And that decay rate is going to have to be less than 1. We can actually think about taking 100, subtracting 2.1, and you would get 97.9 or percent. Okay, these are all percents. And then as a decimal, that's 0.979. And we want to know it in 5 years, so that's the calculation we'd use. This is an exponential decay example, so I plug that into my calculator, and it gives me an answer of around 56,837. Okay, kind of applicable to what's going on right now. Suppose that 250 people in a city are infected with a cold virus. Each one of those people infects, on average, 3 other people over the course of 1 week. If this continues, calculate the number of new infections in the 8th week. So we've got an initial amount, 250 people, and we have a growth rate. In this case, 3 other people would mean that they're tripling each time. So our equation, or our calculation, our initial amount times our growth rate, in this case of 3, times to the power of 8 is going to give us the answer for the 8th week. And since 3 to the power of 8 is such a big number, you end up getting a massive number, 1,640,250 people infected in the 8th week. That might seem a little surprising, but it has to do with the fact that, like I said, multiplying by 3 8 times, things get big very quickly. And that's just the number of new infections that week. It's not the total. The total would be even more. It'd be adding up all those other weeks. Now suppose we change this a little bit. Suppose instead of infecting an average of 3 other people per week, the average is lowered to 0.8 people. So on average, each person passes the cold on to less than one person. Now calculate the number of new infections in the 8th week. We actually just change this to an exponential decay question. Our initial amount is still 250, but our growth rate of 3 is now a decay rate of 0.8. And this calculation right here is going to give us the answer for the number of new infections that week. Let's take a look. If you put that in your calculator, you'll get an answer of about 42. So only 42 people being infected with the cold virus that week, as opposed to 1.6 million. So I think that the goal of this is to kind of explain social isolation and the reason that we're in the situation we're in right now, and this kind of being the goal. Okay, one last problem to look at with you. Given some data, so I've made these numbers up, or I've kind of rounded them just for the sake of our lesson here, but the population of Calgary growing exponentially, and you see the years 2005, 2006, 2007, and the population, and we're going to come up with an equation and prediction for the year 2015. So here we are not given the growth rate. We're given an initial population for the year 2005. What's the growth rate? Well, it's not that hard to calculate. We want to know what are we multiplying by each time. Well, to figure out what that answer is, we could divide. And that will give us a growth rate of 1 point. Let's just use my calculator to figure that out. So I get this number here, 1.061207. I'm going to round that somewhere. Let's just say 1.061, which corresponds to a 6.1% increase each year. Now, in order for this question to not be flawed, we should get the same thing when we divide the population in 2000 divided by the population in 2006. I'll let you check that out, but let's assume that it works out basically perfectly, so that we can come up with our population equation. Our initial amount, 895,000 people, okay, times 1.061 to the power of the year, and we'll subtract 2005. And then what we can do is we can answer the next part of the question, which was what about the year 2015? Take 895,000, multiply it. Okay, 2015, we're going to get 10 here, and we use our calculator to come up with that estimate. And we get an answer of about 1.6 million when we do that. Now, one question I asked earlier that I said we'd come back to is, what about the graphs for some of these situations? What do they look like? So let's just take a look at a couple of those right now. Yes, let's talk about the graphs of some of these equations. Starting with the Snapchat party, y equals 3 to the power of x. I've graphed this in Desmos. Here you can see it right here. I've had to change the scale because I need lots of big y values here. And I've only included the values of x greater than 0. You can see that it's a steep upward climbing curve, which is what an exponential curve looks like. The next example that I'll do is the contagious disease, which was y equals 3 times 2 to the power of x. And y equals 3 to the power, it looks like that. Very similar. Here, let's put them. The blue one is the 3 times 2 to the power of x. If I put it against the Snapchat one, you can see that they're somewhat similar. And moving on to the, let's do the grocery store job, $15.25 an hour with a 4% raise. What does that look like? Well, that looks like the green line. Now you see that that looks more like a straight line. It has a very low growth rate compared to a growth rate of 2 or 3. But look what happens as I zoom out. Sure enough, eventually it has that same steep climbing curve. My point I want to make is all 3 of these exponential growth examples, they kind of look the same as long as you zoom out enough or zoom in enough or whatever you need to do. How about exponential decay? We talked about the value of the car depreciating at 20% per year. So that's 65,000 times 0.8 to the power of x. That's what that looks like right there. Okay, now obviously we need to go up quite a bit to see the beginning of the graph, but it's kind of like the other examples, only sort of flip the other way around. Instead of going up, it's going down. It has that same sort of shape otherwise. And then we can include the population of Detroit. Now I'm not going to see anything now. I need to change my scale because we got to include a lot of people here. Need to go up all the way up to 1 million, basically. And we can see that there's that similar shape for the population of Detroit. So that's what those graphs look like. We're going to talk more about that later on. In the meantime, I've got some problems for you to try, and I encourage you to do those, and I'll see you next time. Thanks.